So today we're going to do a review for exam number 4 on chapter 6 and 7. And when, let's see, look at the schedule. Right. On Thursday, exam 4 will be due, and we'll start with chapter 9 at that point. And that'll give us time to cover chapter 9 and get a review in, and then you'll have all the spring break to prepare for the exam on chapter 9. Okay. So I'm going to work from our review document. I need to share that. I can remember where I put it. Here it is. And there we go. Okay, that should be big enough to. I could make it a little bit bigger, I guess. It's not just so that we can see it, but that when YouTube gets through processing the videos, sometimes the quality is not as good as you expect. So the bigger, the higher resolution you can go in with, the better off you are. Okay. So I've got some of these problems identified as pivotal, but we may deviate a little bit as we go along because we've got plenty of time to cover this topic and any questions you might have, which we should do first. If you've got any questions, the burning issues that are bothering you right now, we'll get those done first. All right. I think I just was looking at number 2. Why did I mark that bonus? And then when I read the question, I see that's a topic we haven't covered yet. This is stoichiometry. It'll come in the next chapter. So we probably better leave that one alone for now, except maybe to balance the equation. We could do that. So why don't we do that? Let's take that number 2, and we'll not answer the question as it is, but we'll balance the equation. So C12H22O11, and we'll recognize that as sucrose, table sugar. C12H22, yep, and O11, and then we're going to burn it. Actually, when you eat table sugar, this is the reaction that occurs in your body. Oh, the difference is if you have a tablespoon of sugar and you use a lighter and you catch it on fire, it'll burn. But that wouldn't be too healthy for your cells if it released energy that fast. So our cells go through a stepwise process to extract energy from that molecule. The end product is the same. Overall reaction. Let's see, I better leave myself a little bit of room here for coefficients. There we go. All right. So we know that's not balanced because there are 12 carbons here and only 1 carbon there. So this is one that you probably want to use the budgeting procedure for. Identify your elements and put them out here. So there's carbon, hydrogen, oxygen. That's it. We start off with 12 carbons, 22 hydrogens, and 11, 12, 13. 13 oxygens. Now let's see if I counted them right. So that's 13, 35, 47. So that's 13, 35, 47. That's good. Now on this side we have 1 carbon, and we have 2 hydrogens here, and we have 3 oxygens. Okay, so that's our initial tally of the number of atoms of each element on either side of the equation. Where do we start? Well, the first thing you want to do is hold in reserve any element that is not bound to anything else. A pure element, oxygen. Leave oxygen till last. If you don't see any obvious place to start, and that's only gained from experience, then just start at the top. So we have 12 carbons here. What if we need 12 carbons over here? Right. So that gives us 12 carbons. It also gives us 24 oxygens, 25 oxygens. Okay. Hydrogens. How about hydrogens? Let's see. Hydrogen occurs in one place here and one place there. That's good. So if we need 22 hydrogens, if we say 11 times this one, that should give us 22. Right? It also gives us 11 oxygens and 24 oxygens is 35 oxygen. Yeah, 35. Okay. Now we can balance the oxygens last because we have this free oxygen here, and we don't want to touch that one if we can help it. Because if we mess with this one, it changes the others. So how would we get, how many do we actually need? Right? Well, 11 are spoken for. So 11 from 35 is 24. So we need 24 more oxygens. So how about 12? Right? 24 and 11 is 35. So that looks to me like it's balanced. And that's the beauty of this budgeting system. You can tell in an instant whether you're balanced. And then, of course, if your grade depends on it, you want to check yourself. 12 carbons, 22 hydrogens, 24, 35 oxygens, 24, and 11 is 35. So we're balanced. We'll leave the rest of this problem until the next chapter, because we have to discuss the topic of stoichiometry. That's a big word, but it's a useful skill that we'll learn in the next chapter. All right, I'm going to mark these off as I go. Got that one. Yeah, let's try this one, number 3. We're starting off with, what's that compound? Phosphorus pentachloride. And we're combining it with water. And we're going to get H3PO4. Since we've got water here, then we probably want to name that with the acid naming convention. So that would be phosphoric acid. And then HCl, hydrochloric acid. Okay. So we don't have any free elements to hold in reserve. Typically, if you have water available, you'll try to hold that one. But we also can't use the trick where you have the polyatomic ion, because the polyatomic ion was actually formed in this process. So we have to treat every element independently. We've got phosphorus, chlorine, hydrogen, and oxygen. So we do our initial tally. We have 1 phosphorus, 5 chlorines, 2 hydrogens, and 1 oxygen. And on this side, we have 1 phosphorus, we have 1 chlorine, we have 4 hydrogens, and we have 4 oxygens. Okay. Now, where would we start? Well, the phosphorus is already balanced. I mean, that may not hold. I mean, it will probably change, but for now, we can leave that one alone. Next in line is chlorines. Right? So we could go with chlorine. Say we need 5 chlorine. So we put a 5 here. That makes 5 chlorines. And that also changes the hydrogen count. So 5 hydrogens and 3 are 8 hydrogens. Okay. Next one down. We need 8 hydrogens on this side. So if we put a 4 here, that should make 8 hydrogens and 4 oxygens. And as luck would have it, we're balanced. 1, 5, 8, 4. Now to answer the question, what's the coefficient in front of hydrochloric acid? Well, it's 5. Right? D, 5 is the answer to that one. Okay. How about number 4? Which one of these is not a clue for a chemical reaction? How about a solid forming? What do we call that? Precipitation. If precipitation is occurring, you've got a chemical reaction. How about the reactant is smaller? What do they mean by that? Does that mean the amount of reactant becomes less? Can we say with the reactant becoming less that we have a chemical reaction? Not by itself. There are physical ways to reduce the amount of chemical reactant without producing a reaction. For instance, if your reaction involves oxygen as one of the reactants, all you need is a leak and your oxygen's gone, but there's no chemical reaction to reduce that amount. So B by itself would be the answer to the question, because it's not but in and of itself an indicator of a reaction occurring. Now, if bubbles are forming, and of course you've got a contained environment, bubbles forming does indicate the production of a gas, and that indicates a reaction. Color change occurs. That one's a tricky one. Color changes can occur. Well, actually, no. A color change does indicate a reaction. If the color becomes lighter, for instance, it may just be a consequence of dilution. You just add more solvent and the color becomes less intense, but the color doesn't change. Now, from visual inspection, you can see that happening. If you have an instrument available, you can actually measure the wavelength or the wavelength profile of the of whatever is causing the color, and you can find from that whether or not an actual different color is being produced. It's called spectrometry. A flame occurs, yeah, that's a pretty good indicator there's a reaction. And you can feel the heat, or you can feel heat being drawn from your hand if you touch some object that's in which a reaction is occurring. Okay, so let's see. Let's take this one and we'll go beyond the question. First, we'll balance it. So balance this equation, and then we're going to talk about it a little bit. We may talk about it while we're doing it too. I forgot to number my problems, so I'll start numbering them. So we've got aluminum. We got this version of an oxide of iron. Okay. So this looks to me like it's the my mind's gone blank. I'll think of it in a minute. But I would point out that there's an element, there's a compound. There's an element, it's in a compound here. So we know what type of reaction this is. Well, actually, it's one of two different types. This is an oxidation reduction reaction. You've gone from zero oxidation state here to an oxidation state of 3+ here. So in order to get there, you had to lose 3 electrons for each aluminum. And similarly, you're going from this iron in a compound to that free iron, and that's also an indicator of oxidation reduction reaction. The problem with this formula is the oxidation state of iron is not a whole number. So I'm suspecting that this is a composite of a couple of different compounds that are possible, right? Because if you say oxygen is 2-, and you can tell that from the periodic table, right? The charge on oxygen over here is going to be 2-. So 1- for the halogens, 2- for the chalcogens. So that means you have 8 total minuses here. Well, you have to balance that with 3 irons, right? So if you got 8+ that has to be over there, each iron is 8/3 of a positive charge, which doesn't happen. I mean, it doesn't happen in our accounting scheme. So my guess is it's a combination of 2 different compounds. Nevertheless, I just remembered. This might be the thermite reaction. There's another possibility. Thermite could be this one. In that case, the oxidation states do, and the charges for these are whole numbers. But let's take what we've got and see if we can balance it. Okay, so we've got aluminum, we've got iron, and we've got oxygen. We've got 1 aluminum, 3 iron, 4 oxygen. We've got 2 aluminum, 1 iron, and 3 oxygen. Okay, we've got aluminum as a free element on one side and iron as a free element on the other side. We want to hold those to the end and see if we can do any balancing with the compounds. Notice with the oxygens, 1 in each compound, this is an odd and that's an even. So when that happens, sometimes the best trick to use is cross multiply. Say, take that 3 and put it over here. And take that 4 and put it over here. So that will give you 12 oxygens here and 12 oxygens there. Okay. What does that do to the rest of the irons over here? Makes 9 irons. And the aluminums makes 8. Okay? So now we can use our free elements to finish the balance. If we need 8 aluminums, we just put an 8 here. And if we need 9 irons, we just put a 9 here. And we're balanced. That cross multiply thing is a trick that I didn't put in the useful, the hints. But it does come up from time to time. Okay, and I think I discussed the topics I wanted to. What type of reaction? Oh, this is also what other type of reaction, where you have this element substituting for that element. So you put that one in there, kicks that one out. Now this one is free. That's a single replacement reaction. It's also an oxidation reduction reaction too. Oh, we answered the question. Coefficient of iron is 9. So that makes A the answer. All right. So we got that one out of the way. We actually did a slide on this one in the lecture. So the only statement in here that's false is when you balance a chemical reaction, all the subscripts must be conserved. It's wrong. The subscripts are established by writing the correct compound or element, as the case may be. And then you don't touch the subscripts after that. Once you've written the compound correctly, then the subscripts are off limits. The only way you can balance an equation is with coefficients. Here we got another combustion. That one should be fairly easy to do. Let's do that one, number 7. I think there's a trick involved here that will be a useful reinforcement. So we've got C2H6, that's ethane. Methane is CH4. Ethane is the next one with 2 carbons, C2H6. Beyond that is something a lot of people use every day, propane, C3H8. We're going to use ethane in this one, C2H6. Combustion, oxidation reduction. And we get carbon dioxide and water every time. Well, not every time, but if it's complete combustion, if it's not incomplete, like inside your automobile engine. But if it's complete combustion, you always get carbon dioxide and water. Okay, so our budget has carbon, hydrogen, oxygen. We have 2 carbons. We have 6 hydrogens, 2 oxygens on this side. And on this side, we have 1 carbon. We have 2 hydrogens. And we have 3 oxygen. Okay, we could start with hydrogen or we could start with carbon. I'm inclined to start with carbon because we only need 2 over here. That gives us 2 carbon and 5 oxygen. Okay? And we're holding oxygen on this side till the end to do the final corrections. So now for hydrogen, we need 6 on this side. So we'll put 3 here. And that makes 6 hydrogen. It also makes 3 plus 4 is 7 oxygens. Carbon and hydrogen are balanced. Now all we have to do is get 7 oxygens out of that. So how do you do that? No whole number is going to do it for you. We have to use the fraction trick. So if we say 7 halves of an O2, we get 7 oxygens, right? Because a half of an O2 is 1 oxygen, and 1 times 7 is 7. Now we need to convert it to whole numbers. So we use a multiplier. You just take the denominator and put it out here, and that cancels that one and puts a 2 here and puts a 4 here and puts a 6 there. Okay? So to answer the question, what's the coefficient of the underlined one? 7. We canceled the half, so now it's a whole number 7. Right. So let's look at number 10. Here we go. Okay, number 10. We're looking for the coefficient of water in this one. So let's conduct this reaction and see what kind it is. Killed 2 birds with 1 stone. Al2O3, what is that? What naming convention would that be? Aluminum is a fixed charge. Right? It's in that 3rd group from the left. It's always a 3+. So that's a type 1 compound. So all we have to do is say aluminum oxide. That's it. We're done with that name. And I'm leaving out the phase indicators for these because we're interested in balancing. H2SO4 is sulfuric acid, right? That's the sulfate ion. H's become X. And if there's oxygen in it, you don't say hydro, so you say sulfate becomes sulfuric acid. Then we have Al2SO4. Al2SO4 with a 3 subscript because sulfate is a polyatomic ion. You can't mess with the subscripts. You have to use a parentheses. So with a 2- charge here and a 3+ charge there, you cross multiply. 3 here, 2 there. That's your balanced compound. And then we have water. Okay, let's do our tally. Notice that we have sulfates here and sulfates there. We can use sulfate as a balancing instrument. This oxygen will be balanced by that oxygen. So if we have aluminum, we have some oxygen, we have some hydrogen, and we have some sulfate. Okay, so we set up our budget. We have 2 aluminums, 3 oxygens, 2 hydrogens, and 1 sulfate. And over here we have 2 aluminum, we have 3 sulfate, we have 2 hydrogens and 1 oxygen. Okay? At this point, aluminum and hydrogen are balanced. We don't have any separate elements for it to hold till in reserve. So let's look at oxygens and balance oxygens here with that molecule. I'll tell you what. Let's do sulfate first. I think it'll be easier. And this only comes from experience. If you're not balancing several equations every day just to get practice, then you're shooting yourself in the foot. It will come back to haunt you. So we need 3 sulfates over here. And that changes the number of hydrogens to 6. Okay? Now we can go over here and say we need 6 hydrogens. So that makes 6 hydrogens. It also makes 3 oxygens. Okay? So that approach did get us to the finish line quicker with less trouble. We could have taken my original course and done the oxygens first. And who's to say that it might have been just as simple? But we would have got there eventually. Okay. What type of reaction is this? I'm inclined to think that this reaction is acid-base. And here's why. There's your acid. We don't recognize this as a base because it's a solid. But we do get a combination of a cation anion over here, which is characteristic of a salt and water. So that's why I'm saying it's probably acid-base. And this is a basic entity, although it's not dissolved in water yet. Aluminum oxide is not soluble in water. So that means that the acid here has to attack the surface of the solid. Although, when we say insoluble, sometimes we mean slightly soluble. I mean, maybe 10 to the minus 10th of that amount goes into solution. And that's all that's required, because once you remove that from solution, then there's more come to replace it. Okay, so the answer to that one would be B, 3. All right, that was 10. Let's go to, mark that one off. We'll skip a few, it looks like. Um, 26 is another case of a bonus. And what's happened is, for some reason, the test bank where I got these questions, several of these snuck in and they had indication, they required information that we hadn't covered yet. So I marked them bonus in case you were inclined to go look them up. So 26, let me back up here. 26 is a bonus because it's covering a topic we haven't introduced yet, not till next chapter. But if we balance this equation, we've already balanced that equation. Ethane reacted with oxygen, makes carbon dioxide and water, right? So that it's already balanced from a previous problem. So let's move on down to 33. So let me see if I can get there quicker. There we go. All right. Since this is the key, you've got the balanced equation there, but we're going to work from the word problem. And if you get a word problem like this, that's where your ability to name compounds and write the compounds from the name comes into play. So write and balance the equation, showing the reaction of iron 3 oxide. Right? We've got the Roman numeral in there telling us the charge of iron, and that's accurate because iron is a transition element, and it can have more than one charge, so we have to say what it is. So iron 3 oxide, iron has a 3 plus, oxygen has a 2 minus. So we have an odd and an even, we just bring the 2 down here and the 3 down here. And that's the first reactant. Then we're going to react that with carbon monoxide, which is a type 3 compound. You just say how many there are. There's 1 carbon, and mono means 1 oxygen. Okay? So then it also gives us the products, right? You don't have to guess at that. It forms iron metal, which is the element, and carbon dioxide. Okay, now we want to balance this equation. Right? We have a free element here that we want to hold to the end. Right? That just makes sense. We're going to set up our tally. There's iron, there's oxygen, and there's carbon. So we have 2 irons to start with. We have 4 oxygens. We have 1 carbon. And on this side, we have 1 iron. We have 2 oxygens. And we have 1 carbon. Okay. We have oxygen in 2 different places here. So that could be a problem. The fortunate part is we've got an even number of oxygens on this side and an even number on that side. So it makes it easier to balance. All we have to do to balance the oxygen is put a 2 in front here. But I can see a problem brewing right now. We've also changed the number of carbons. Right? So that's probably not the best course. Maybe we should focus on there's no choice. We have to do oxygens. But we've got to do it in such a way that the effect on carbons can be absorbed in this process. Now, actually the best way to balance this equation is to use a redox, right? And I'm going to show you how to do that. You just need to know what are the charges. Right? We know that the charge here is 3 plus. We know the charge here is 2 minus. This is 2 minus. So that makes this one 2 plus. Right? This one is 2 minus, which makes a total of 4 minus, which means this one has to be a 4 plus to balance it. Right? So you can see that we've gone from 2 plus to 4 plus, and that carbon has lost 2 electrons. This iron, all free elements are 0. They don't have a charge. Right? So what we've gained here is we've gained 3 electrons for each iron. So if we do it like this, and I'll show you that we've gained 3 electrons per iron. And here we've lost 2 electrons per carbon. The thing about oxidation reduction reactions is the number of electrons that are lost has to equal the number that are gained. In this case, we've got 3 versus 2. So we've got an odd and an even, and the best way to handle that is the cross multiply again. So if we multiply this one times 3 and this one times 2, we have 6 electrons transferred and 6 electrons lost, gained. Now, how do you get 6 electrons out of this? Well, you need 2 irons. Right? You got 2 irons here, so we need 2 irons there. Right? That takes care of 6 electrons gained. How about 6 electrons lost? If we go from 1 carbon being 2 electrons, we need 3 carbons. 3 carbons to take care of those 6 electrons. Now, we have a new starting point. So what I do is I erase all of these and do a retally. Sometimes the retally shows that it's already balanced. So how many irons? We have 2 irons here. We have 6 oxygens, and we have 3 carbons. And over here we have 2 irons. We have oxygen, 6 oxygens, and carbon, we have 3 carbon. It's already balanced. And that's really the easiest way to do it, is to balance the electrons first. We probably could eventually have gotten there, but it would have taken some real gyrations and mental trickery to get these coefficients to give us the balance that we want. And we probably, without doing electrons, we probably would have ended up with really large numbers up here, and then you'd have to reduce them, divide by a factor to get to that point. But this way you get there quicker. And actually with fewer mistakes. All right. So that was 33. Let's take a look at 40. Let's see, am I still on screen? I'm walking a little bit. Let me pull it back. There we go. Okay, number 40. So 40 actually gives you the starting point equation. It doesn't ask you to write the correct. I better scroll down. There's 40. Okay, let's see. That thing seems to be in the way. I don't know if you can see it, but it's bothering me. Okay. So what is Mg3N2? Mg3N2. That's a class of compounds called nitrides. When nitrogen is the anion in a compound, we change the ending from nitrogen to nitride. And nitrogen then, since it's 3 positions over from the right, -1 halogens, -2 chalcogens, -3 pnictogens. That means that nitrogen is a -3 charge. Since magnesium has to be a +2, it's an alkaline earth, That's 6 pluses, 2 times 3 is 6 minuses, so that's written correctly. Then we're going to react that with water, and that yields ammonia and magnesium hydroxide. Okay? Now we have to balance it. So let's take a look at it first. I don't see any changes in charges. In other words, this is not a redox reaction. Magnesium is the same on both sides, 2 plus. Nitride, nitrogen is -3, and here it's also a -3 because hydrogen is typically a +3. And it's written to the right just out of convention. I know it's to the left of nitrogen, and you would normally put hydrogen first, but in this case, it's always written second. And this is nitrogen is -3. Hydrogen is +1, +1, -2, -2. So we don't have any transfer of electrons. So we just go with what we've got. Magnesium, nitrogen, hydrogen, and oxygen. We have 3 magnesiums here to start with, 2 nitrogens, 2 hydrogens, 1 oxygen. We don't have any free elements, so we can't hold anything in reserve. Magnesium on this side, we have 1. Nitrogens, we have 1. Hydrogens, we have 2, plus 3 is 5. And oxygens, we have 2. Okay? Now, do we have any elements that are in 2 different locations, like that last one we were doing? Let's see. No, that's 1 location. That's 1 location. Okay. So it should be fairly simple. Should be is the key word there. If we balance the magnesiums first, that means we have to put a 3 here. And that makes this one 3. But it also changes oxygens. We have 2 hydroxyls times 3 is how many oxygens? 6. 6 oxygens. And 2 hydrogens times 3 is 6 hydrogens. Plus 3 hydrogens is 9. Actually, we do. We got hydrogens in 2 different places. That could be a problem. We'll see. We'll cross that bridge when we come to it. So how about nitrogens? Well, we got 2 here and we need 2 here. So this makes 2 nitrogens. Now we recount our hydrogens. 6 here and 6 there is 12 hydrogens. Okay? Now if we want to get 12 hydrogens out of this, we need a 6, which makes 12 and 6 oxygens. And we're done. It's 1, 6, 2, 3. That one wasn't too bad, I guess. All right. Let's see. Let me mark that one off. And we're going to look at how about well, I skipped quite a few here. Oh, okay. We'll take propanol, number 61. So let me, there we go. There we go. And the authors have been kind enough to write the compounds for you. So this one is 61. And we start off with this compound. Let's see. I'm going to start over here a little bit. C3H7OH. And then oxygen. So we've got a combustion reaction. It's also oxidation reduction. Combustion is a special case of oxidation reduction. And that produces carbon dioxide and water. All right. So we do have oxygen that we can hold in reserve till the end. And now we want to do our tally: carbon, hydrogen, oxygen. So we have 3 carbons. We have 8 hydrogens. Don't forget that one. And we have 2 oxygens. On this side, we have 1 carbon. We have 2 hydrogens. And we have 3 oxygens. All right, where to start? Well, carbon's only in one place, so we could start there. Hydrogen is only in one place. We could start there. I'm inclined to start with carbon. If we put a 3 over here, that gives us 3 carbons. It also changes to 6, 7 oxygens. Okay? Now how about hydrogens? We need 8. We've only got hydrogen in one place, so if we say 4, that gives us 8 hydrogens. Now it changes the oxygens. 4 plus 6 is 10, correct? 6 and 4, 10. Now we need 10 oxygens over here. And we're done. Let's see. What did I do wrong? Did I write these correctly? 3, OH, oxygen, carbon dioxide, water. Let's do a recount. 3 carbons, 3 carbons. 7, 8 hydrogens, 8 hydrogens. 1, that's it. That's where I made my mistake. That oxygen plus this makes 3 oxygens. So I'm going to have to backtrack. So we had 1 and 3. And hydrogens, we had 2. Okay. So now if we go back and correct my mistake, well, actually, this is okay. We can do 3 carbons here. We've got to get rid of that one. Okay. Let's try this again. Now that we've counted correctly, 3 oxygens. This makes 6 oxygens, 7 oxygens. There we go. Hydrogens. So we can put a 4 out here for hydrogens and make 8. Okay. So now we've got carbons balanced, hydrogen balanced. We've got to balance oxygens. We need 7 oxygens. But let me count again. 6, no. 4 and 6 is 14, correct? No. can't count. 6 and 4 is 10. Okay, let's check to be sure. 3 carbons, 3 carbons. Hydrogens, 8 hydrogens, 8 hydrogens. 1, 3 oxygens, and 6 and 4 is 10 oxygens. Okay. We need 10 oxygens on this side, but one of them's already spoken for. So we really only need to get 9 oxygens out of this one, which means we need to do 9 halves. So that means 9 plus 1 is 10. Now we got to get rid of that half. That makes this one 2, this one 9, this one 6, and this one 8. 2, 9, 6, and 8. 2, 9, 6, and 8. Okay. See how easy it is to make a mistake? That was 61. That's probably why I marked that one. Let's see who's next. 68. I think we're still in chapter 6 also. We haven't gotten into chapter 7 is the next page. So we'll go to 68 and then we'll get into chapter 7. Six, one more page. There it is. This one looks familiar. I wonder if I've already done this one for you. C8H18 is octane. That's the stuff you burn in your gas tank. C8H18 plus oxygen yields carbon dioxide and water. Okay. Hold that one in reserve and do our tally. Carbon, hydrogen, oxygen. So we have 8 carbons, 18 oxygens, hydrogens, excuse me, and 2 oxygens. Over here we have 1 carbon, 2 hydrogens, and 3 oxygens. Okay, oxygen's in 2 different places. So we probably don't want to touch that one just yet. Let's start with carbon. If we need 8 carbons, that gives us 8 carbons. It also gives us 17 oxygens. Okay, how about hydrogens? Well, if we need 18 hydrogens, and this is the only place you can get hydrogens, we need 9 there. 2 times 9 is 18. And then we have 9 oxygens plus 16 oxygens, which is 25. 25 oxygens. So how do you get 25 oxygens out of a diatomic? Multiply by 25 halves. Now, technically, it's balanced, but it's not the simplest whole number. So we got to get rid of the fraction. That makes this one 2. Makes this one 25. This one is 16, and that one is 18. 2, 25, 16, 18 to balance that equation. Okay. Now, starting on the next page, we get into chapter 7. They're numbered sequentially, right? So we go from 69 to 70. But I know that it's a new chapter, not just because of the material it's covering, but because the point structure has changed. We increased point structure in the previous problems up to a level of 5 points per problem. This one is back down to 1. So I'm thinking that this is the beginning of chapter 7. And if we're talking about solutions, that's another indicator. Chapter 7 is reactions in aqueous solution. Okay, let's see, where do we start? Well, I don't have these marked, but it might be instructive to look at some of these guys. Number 70, a precipitation reaction. Remember what that is? It generally occurs as a double replacement. So generically, we would write this compound in aqueous solution and this compound in aqueous solution. And then we would do a double replacement. So A would replace C. So we would have AD and CB, right? Cation, anion. And typically what happens is one of the compounds is still soluble. Let's just arbitrarily say this one is still soluble. But this combination of A and D is insoluble. That forms the precipitate in solution, and it makes the solution murky. In other words, light doesn't shine through it. And if you wait long enough, the solid that's formed here will settle out. And then the solution that's left over will be, you can see through it. It might be colored. Usually it's clear, but it might be colored. But you can still see through it. It's a bona fide solution. And if you shine a light through the side, remember that? If you shine a light through here, and you look at on the other side, you can see the light beam come through, but from this angle, you see nothing. That's a solution. That's the non-Tyndall effect. The Tyndall effect would be if you have a suspension that still has some solid suspended in the water, you'll be able to see that light beam here. Okay. So back to 70. What happens to the ions that don't precipitate? That one out there that was still in solution. I mean, what do? They stay dissolved in solution. The ions are still free. If you write a compound that says aqueous, well, it depends on the compound, but if the compound is formed from a cation anion, then those two entities break apart and they're in solution, separate. If you dissolve something that's not ionic, like glucose or sucrose or some sugar like that, it won't break apart. So in solution, it's still a molecule. But for this double replacement reaction, we're talking about ions. And the compound that's formed that is still in solution is that's not precipitated is in solution as free ions. Now those free ions were present on the reactant side too, and they're present on the product side. So what do we call them? They're spectators, right? The focus of our attention on that type of reaction is on the formation of the precipitate. That's what drives the reaction. The free ions floating around that don't react, they have nothing to do with the reaction. They're just there. But the formation of that precipitate drives the reaction to the product side. Okay, what type of reaction is this? Well, look at the reactants. Right, what do you have here? That preceding hydrogen, right there, that preceding hydrogen should be a dead giveaway. That's an acid. And this one has a hydroxyl built into it. That's a base. Now, all bases don't have hydroxyls. And when we get to study acids and bases, that will become clear. But for now, most bases have hydroxyls built into their formula. And then what happens? Well, you produce water as one product, and you produce a salt as the other. So you have the cation from the base and the anion from the acid combine, so to speak, and form the salt. Now, sometimes this salt is soluble and sometimes it's not soluble. Example, where you have a combination of an acid and a base and it forms a precipitate, right? So you could have an acid-base reaction and a precipitation reaction. This particular reaction is acid-base. But if we have this one, let's see if I can remember. Sulfuric acid. Okay. And we react that with barium hydroxide. They're both soluble. Then we make the salt, barium and sulfate. Barium, sulfate. That's a 2 minus, that's a 2 plus, so that's the way you write it. And water. Barium sulfate, look it up in your chart. Remember, at the back of the, you have a solubility chart at the back of your useful information. Where is it? Here it is, right here. This one right here. Let me confirm. Barium hydroxide is soluble. Barium sulfate, here it is. Barium sulfate is insoluble. So here you have an acid-base reaction and a precipitation. Well, technically you have a double replacement too. Right? That replaces this, combines with that, and this replaces that, combines with that. So all three of those are accurate descriptions of this reaction. Now this reaction is not balanced, correct? Right? Because you have two hydrogens here that could combine with these two, which should make 2 waters. Right? 4 hydrogens, 2 plus 2 is 4, and 2 oxygens. And this barium sulfate, that's balanced. You only need one of those, one. So we're good there. That's balanced. All you have to do is add a coefficient to water and you're balanced. Okay, that's an example of an acid-base reaction that involves precipitation as well. Okay. Let's see. 72. What if you mixed a solution of potassium chloride and sodium nitrate? What would you get? Well, double replacement, right? Sodium goes with chlorine. Everybody knows sodium chloride is soluble, table salt. And potassium nitrate. That's soluble too. So when you mix those two together, you get no reaction. Everybody's in solution. They started in solution, they stay in solution. There's really no reaction, nothing driving the formation of some product. So that's why E is the answer to that one. Now, when you're given a situation like this, number 73, and I'm doing it again, I'm not writing the numbers up here. 73. If the question is, what solid is formed in the balanced equation? Look at your answers. All right, there are no coefficients in front of those. So all you really have to do is identify the compound. So if you're taking ammonium carbonate, ammonium is like this, carbonate is like that, right? We don't even have to write the compound correctly. We'd need two of these to go with that, of course. But then you react it with nickel 2 chloride. So nickel 2 is that, and chloride is that. So we say, how do they interact? Well, ammonium, two cations don't react. Two anions don't react. So we have nickel and carbonate, right? 2 plus, 2 minus. And we have ammonium chloride, 1 plus, 1 minus. So those are the two possibilities. Just look them up, right? See if they're soluble. All ammonium salts are soluble. Nickel carbonate, look that one up. That one is insoluble. So that's why B is the answer for this one. Let's see, can't do it. Oops. There. Nickel carbonate is the solid that's formed in this reaction. All right, we're going to get some reactions that we need to classify. Now, since these will probably be in the multiple choice question format, regardless of what you have identified as the true classification, multiple classifications perhaps, of a reaction, you look at your selections, which of those are available. So in this case, we have 2 magnesium, solid, plus oxygen, gas, yields what? Another solid. Okay. Now, you're probably too young to remember, but when cameras had film in them, and before they had electronic flashes, you had film in your camera, and the only way that you could take a picture in a dark room was to use a flash bulb. Use it one time, throw it away. Inside that flash bulb, you could look in there and see these fine filaments of what appeared to be a metal. And all you had to do to get that metal to react with the atmosphere that was inside, which had oxygen in it, and the metal was magnesium, very thinly shredded magnesium in that bulb. So when you hit it with a direct spark that initiated the reaction, magnesium burned and gives off a lot of light, huge amount of light, because it burns fast too. So that's this reaction inside that flash bulb. And the landfills are probably full of them now, but we don't use them anymore, fortunately. That was one of the first things to go with film cameras. They converted to electronic bulbs, so you could flash many times. You just have to build up a charge in a capacitor and then discharge it through your little bulb, and it would flash. And then you build up the capacitor again and flash it again. So that eliminated that waste, but we still had film. And in many respects, film is superior to solid state detectors that are in cameras now. Simply because film is it's continuously variable. In other words, when the image is impressed upon the film, you get a whole range of intensities, colors, the pixel size, the resolution of your picture on film is limited only by the size of the grain, the silver grain that's in there that detects the light and promotes the reaction. So you can make that, at least for a long time, you could make that grain a lot smaller than you could a pixel in a solid state detector. Now the solid state detectors are actually, many of them exceed the resolution of film. The only drawback with film was the very high resolution films were slow. They had slow speed. They need a lot of light or a long exposure to react. Whereas with solid state cameras, you can have that high resolution and just, it's like motion picture. Okay, back to the problem. Classify the following reaction. Well, let's see, what is it really? Well, you've got an element there, both in a compound. This is definitely a redox. And it's got oxygen here, so that's a combustion. Right? We got simple going to complex. So we have a synthesis. There's another name. Combination. Okay. Those are the three that I can think of. So let's see what we have to choose from in our answers. Synthesis is there. Oxidation reduction is there. Combustion is there. Let's see, we're missing a choice. Must be on the next page. There it is. A through C are all correct. Every one of those is a classification for this reaction. Okay, looks centered. Let's see if we got another one that we can choose from. This is the definition, 75. What do we call a substance when you dissolve it in water? It produces a solution that will conduct electric current very efficiently. And so there are two things. It'll conduct electricity, but it does so very efficiently. Well, if it conducts electricity, we call it an electrolyte. Now, what does it have to do to be an electrolyte? When the compound goes into solution, it has to break apart into free ions. If it makes those ions, then the circuit can be completed between two electrodes that are placed in the solution. If there are no ions to carry the current from one electrode to the other, then it's a non-conductor, like pure water or sugar. Put sugar in water, it will not conduct electricity. Any covalent compound that goes into solution will not conduct. There are some, in this case, if it's very efficient, it's a strong electrolyte. Right? So that's why D is the answer. If it only partially ionizes, then it could be a weak electrolyte. Like some acids are like that. Acetic acid, vinegar. Is a weak electrolyte. All right, that was 75. Okay, we're doing good on time. Probably going to finish early, actually. 75, I just don't want to backtrack you. All right, what type of reaction is 76? So we got silver oxide and, oh, what is it doing? It's giving us silver metal plus oxygen. All right. So what type of reaction is that? Compound elements. It's a redox. Right? It's also going from complex to simple. It's a decomposition. Okay. That's all I get from that one. I can't see any other possibilities. So if you look at our choices, decomposition is there, oxidation reduction is there. It's not a synthesis. That's going the other direction. Synthesis and decomposition are opposites. You can't have both at the same time. It's not a combustion because one of the reactants is not oxygen. Oxygen's a product. So in that case, combustion is not possible. So that's why A is the answer. Just two of them are correct. In what type of reaction is water always a product? Acid-base. Every acid-base reaction produces water. In fact, the production of water for every acid-base reaction is the driving force. Remember, we mentioned that at the very beginning of this chapter 7. The driving force of a reaction could be the formation of water. Now, if you have an acid-base reaction like the one I showed you earlier, where you form a precipitate, where you form a solid, that's also a driving force for that reaction. But all acid-base reactions are driven by the formation of water at the minimum. Transfer of electrons, that's easy. That's an oxidation reduction reaction. That one's too easy. Let's skip that one. All you have to know there is the definition. Which one of these is not considered a common cause of a chemical reaction? A decrease in temperature. If you decrease the temperature, you generally reduce the chances of a chemical reaction occurring. Usually an increase in temperature is required. And that's a discussion for another day. In fact, I don't even know if we're going to get to that one in this course. It has to do with activation energy. In other words, a reaction needs a minimum amount of energy in order to make the reactants, when they smack together, break bonds and form new bonds. But the rest of them do commonly cause chemical reaction. Transfer electrons, that's redox. Form water, acid base. Formation of gas, it doesn't have a special name. Formation of a solid, precipitation. Those are all potential driving forces for a reaction. Let's see. How about these guys right here? The scientists who discovered the essential nature of acids through solution conductivity studies. It wasn't Priestley, Joseph Priestley. He discovered oxygen. He did it by decomposing mercury to oxide using a big 12-inch magnifying glass. He just concentrated the sun's light on that HGO. And produced the metal plus oxygen, like gas. Let's see, is that going to work? 2 plus, 2 minus. We need 2 here, 2 here. There you go. So now it's balanced. That's what Priestley did. He worked with in that range. Robert Boyle worked with pressure volume. That's what he's famous for, the relationship between pressure and volume. And we'll cover that when we get to gases. Einstein, relativity, obviously. He had nothing to do with this stuff. In fact, he came much later. Mendeleev, his claim to fame was periodic table and showing relationships among various elements that put them in families or groups. And he also used the periodic table and his group theory to predict the existence of elements that had not been discovered yet. The only one left that's even remotely associated that could possibly be is Arrhenius. He discovered the essential nature of acids by measuring their conductivity. Okay, so let me see if this one's worth stopping at. Yeah, let's stop at this one, 84. The reason I want to stop here is actually twofold. This problem requires that you know how to write the compounds. If you can't write the compounds, then you can't balance the equation. So hopefully this will impress upon you the necessity for learning how to write compounds. Aqueous solution of ammonium sulfide. Right? This is a 2 minus, this is a 1 plus. Actually, I should have written that out here. Give myself some room. And that's aqueous. And we combine that with barium chloride. Right? Barium's an alkaline earth, 2 plus charge. Chlorine's a halogen, -1 charge. So you need 2 of them. And this one's aqueous. Okay? I didn't leave myself enough room. So I'm going to have to, let's see, they want to balance this equation, don't they? Maybe I better rewrite it so I can do it straight across. Ammonium sulfide aqueous plus barium chloride aqueous yields. Now, how do you know what the products are? Because this is a double replacement reaction. This is one of the types of reactions. This one plus acid-base reactions that you should be able to write the products knowing only the reactants. So we say ammonia combines with chlorine. And you look it up. It's soluble. Most chlorides and all ammonium compounds are soluble. So this one is aqueous. And then the other is barium sulfide. Barium is 2+, sulfide is 2-. And you look it up in your solubility chart and you find that it's a solid. So we formed a precipitate. So what's the coefficient of the solid? So they don't tell you that they tell you there's a solid there, but they don't tell you what it is. What it is barium sulfide. Now we have to balance the equation. All right, so we have ammonium. Ammonium's on both sides. So we can use it to balance the equation. Sulfur, barium, and chlorine. So we have 2 ammoniums. We have 1 sulfur, 1 barium, and 2 chlorides. And over here we have 1 ammonium. We have 1 sulfur, barium. We have 1 barium, and we have 1 chloride. So what we need is 2 ammoniums and 2 chlorines on this side. So that's 2 and 2. And we're balanced. In fact, with practice, you don't even have to do the chart. For these types of reactions, you can balance them in situ, as we might say, without doing the budget. So what's the coefficient of the solid? Is there a coefficient out there? Yeah. If you write that compound, there's at least one of them. So we don't write the 1 right there. So the coefficient for that compound is 1. All right. That was 84. And I stopped there to emphasize the fact that you need to know how to write these compounds. Okay, we could do this one. This equation, it's given to you in balanced form, right? I think we might have done this one already. It says that's an oxidation reduction reaction. True or false? Well, we know we can classify this as oxidation reduction because there's oxygen there and it's in a compound over here, plus oxygen's a reactant. And we have a combustion reaction, right? All combustions are redox. So it's true. It's either A, B, C, or E, right? Can't be D. Double negative, it's not false. So why? Well, let's see. If we take, I guess I better show you. If we take this reaction, and there's 7 of those, and 4 and 6. What are the charges, or what we would call normally oxidation states, for each one of these? Well, free elements are always 0. There's no charge there. Oxygens in a covalent compound are generally 2-. 2-, 1+. So this carbon, since there are 4 minuses there, 2 times 2- is 4-, this one carbon has to absorb all of that. So it has to be 4+. This hydrogen is going to be 1+, so that's 6 pluses. And these 2 carbons have to absorb that 6+, so each one of these would have to be a 3-. All right, 2 times 3- is 6-, balances a 6+. Okay. So we're going from oxygen 0 to oxygen 2- in two places, right? So it gains electrons, which means it's reduced. Remember oil rig? Oxidation is loss. Reduction is gain. So if we gain electrons from here to here, oxygen is reduced. Now, which one of these claims that oxygen is reduced? Let's say oxygen is reduced here. Oxygen's oxidized? No. Carbon, hydrogen. Okay, oxygen is reduced. That's the only one that has oxygen reduced. So it's probably, no, wait a minute. Oh, it doesn't mention oxygen here. Wait a minute. That's not right. Hydrogen is not reduced. That's an error. Oxygen is reduced. And you know, if you have reduction, you have to have oxidation. They come in pairs. So which one is oxidized? Well, we lose 3 electrons from here. Actually, we lose 7. We go from a 3- to a 0 and a 0 to a +4, so we have to lose 7 electrons. So carbon is oxidized. Oxygen reduced, carbon is oxidized. Oxygen reduced, oxygen is reduced, carbon is oxidized. E should be the answer to this one, right? That's wrong. Oops, E. E should be the answer to that one. I don't know how we got B in there. Okay. Okay. That was 85. This is a good, 86 is a good one. Right, in this balanced equation, right, you can check yourself. Zinc, solid, and silver nitrate, 2, silver nitrate, aqueous, yields zinc nitrate, and silver. Okay. The oxidation state, or the charge, is 0 for that one and 0 for this one. We know it's a redox reaction. Element here, compound there. So what's the charge on nitrate? Well, it's a -1. So that means this silver has to be a +1. No choice. Has to be that. This nitrate is a -1. And this zinc, to balance 2 minuses, has to be a 2+. Okay? So we've got silver going from here to here with a gain of electrons, right? To go from a 1+ to a 0, you have to gain 1 electron to balance that +1. So we gain reduced silver here. We gain 1 electron per silver. But how many silvers do we have? We have 2. So that's 2 electrons. Now, that will answer your question, but let's be sure. So if we have a gain here, there must be a loss somewhere else. So this zinc has a loss of 2 electrons per zinc. And there's only 1 zinc, so that's equal to 2 electrons. Right. So the transfer in this reaction is 2 electrons. Okay? All right. Let's see, that was 86. Which one of these is not true? 87. Can we assume when a metal and a non-metal react? Now, there's also another assumption. When we say a metal and a non-metal react, that means the elemental forms. When the element metal reacts with an element non-metal, that will produce an oxidation reduction reaction. When 2 nonmetals react, can they undergo an oxidation reduction reaction? Yeah, it's entirely possible, and it happens. In fact, if it didn't happen, we wouldn't be alive, because most of the biochemical reactions that occur in your body are redox reactions, and they occur among nonmetals. Now, there are metals that are involved occasionally, but for the most part, it's a non-metal. So B is true. C, a metal-non-metal reaction involves electron transfer. That's just another way of saying A, oxidation reduction. When 2 nonmetals react, the compound forms ionic. Never. It cannot happen. Because in order to have an ionic compound, you have to transfer electrons from one to the other. And that never happens between nonmetals. Because the pull, the electronegativity, is not strong enough for one to win over the other. So they share. So D is false. And then E, when a metal reacts with a non-metal, ionic compound is formed. Yeah. For all intents and purposes, yeah. Okay. This is a good one. How many of the following are oxidation reduction reactions? React a metal with a non-metal, that's redox. Synthesis, when you take elements and make a compound out of them, that's oxidation reduction. Combustion, that's a subcategory of redox. Precipitation, that's not an oxidation reduction reaction. Not just a pure precipitation. I suppose it's possible to have one type, but we cannot say blanket that a precipitation is oxidation reduction. So that one would be false. Decomposition, that's also oxidation reduction, because you're going from compound to element. And in order to do that, you have to change the oxidation state, transfer of electrons. So there are 4 of them. B, there are 4 of them that are true. How many of these are oxidation reduction reactions? There are 4. Okay, now this one, when you react sodium carbonate with magnesium chloride, what do you get? And if you write the complete ionic equation, which of these following species, which one of these is present in the balanced equation? And notice that some of them have coefficients. That means you have to balance the equation and include the coefficient in order to find the correct answer. Right, so we have to write the correct balanced equation And then we have to break it down into the complete ionic equation. So here's 89. Right? And we've got sodium carbonate. Carbonate is a 2-, sodium's a 1+, so we need 2 there. And that's an aqueous solution. Okay. Now we have magnesium chloride. And that's an aqueous solution. Now, what are the products? Well, you swap the sodium for the magnesium and you say sodium and chlorine together. That's aqueous. And magnesium carbonate. Right? 2+, 2-, that's good. That is a solid. Look it up in your chart, and you'll find that magnesium and carbonate combine to form a precipitate. Okay, now we need the complete, actually we need to balance it first. So we have a magnesium, 1 magnesium there, 2 chlorides, we need 2 chlorides. And we also need 2 sodiums, we got them, and 1 carbonate. So that little change is all that was required. Now we need to write the complete ionic equation to find the one that fits in our multiple choice answers. So this is going to break apart into 2 sodiums in solution and 1 carbonate in solution, 1 magnesium in solution, and 2 chlorides in solution. Then we have 2 sodiums also in solution. And I'm going to wrap around 2 chlorides still in solution. And then we have this one that cannot be broken apart. That's your complete ionic equation. Now, which ones do these match? Well, let's see. A, sodium +1. Well, we need a coefficient of 2. So A is not it. 2 carbonates. Nope, we only have 1 carbonate. 2 magnesiums. Nope, only 1 magnesium. Chloride. 1 chloride. Nope, we have 2. E, 2 chlorides. That's the one that answers the question. All right. So let's see. That was 89. Let's see here. Let's try this one. Sometimes these picture questions give students trouble because they don't really understand what's being presented in the picture. Okay, so let me go down to 97. Here we go. All right, we can't see the whole thing here, so let me change the zoom. How about this? Okay, let's get the question read and then we'll scroll down so we can get all the pictures in there together. Which of these drawings best represents the mixing of aqueous calcium chloride with aqueous potassium sulfate when they are mixed in stoichiometric amounts? That is, there are no limiting reactants. We have exactly the right amount of each one present to react completely. So what we need to work from is a balanced equation first. Right? We have aqueous calcium chloride. This is 97. Aqueous calcium chloride and we put together with that potassium sulfate. And that makes potassium chloride that's also aqueous and calcium sulfate. Which is a solid, so it will precipitate. Okay, let's balance this thing. 1 calcium, 1 calcium. 2 chlorides, we need 2 chlorides. 2 potassiums, got them. 1 sulfate, got it. So there's our balanced equation. Now, what is this going to look like in solution? Right, that's the important part. We're going to have calcium ions in solution. We're going to have 2 chlorides in solution. We're going to have 2 potassiums in solution. Well, actually, on this side, we're going to have that many. So this is one solution, like this first one, right there. And then the second solution is going to be this one, 2 potassiums and 1 sulfate. I'll just unplug that phone. Sick of spam. Okay. Now on the product side, you've still got 2 potassiums in solution and 2 chlorides in solution. But now you have a solid. Right? So this is one container separate. This is the other container separate. And when you put them together, this is what you get. All right? So process of elimination, test-taking technique. Look at the drawings. What are we indicating as a precipitate? It's marked here, solid. Right? So the black at the bottom is a solid. That means that the only one of these that can answer it must have that in it. Okay? So we got a solid in, and look at the way these are arranged. A refers to this one up here. A B refers to this one. C refers to this one. Okay? So only this one and this one and this one could possibly satisfy. So A and E are out. Cannot be. Got to have precipitate. Okay, what do you have left? Well, let's look at what went in. Right? 1 calcium and 2 chlorides, is that true? 1 calcium and 2 chlorides, yes. So B could be possible. C cannot be. There's only 1 chloride. D could be. So now we've eliminated everything but B and D. So let's look at the next solution. 2 potassiums and 2 chlorides. 2 potassiums and sulfate? Nope. Wait a minute. Oh, excuse me. I was looking at the wrong one. Pardon me. 2 potassiums and 1 sulfate. Right. 2 potassiums and 1 sulfate. B could be it. D, 2 potassiums and 1 sulfate. That could also be it. Right. So we're still B or D. Now I have to look at the products. So let's see what we got over here. 2 potassiums and 2 chlorides. 2 potassiums, 2 chlorides. B is probably it. They're not here in D. Right? Calcium and sulfate ions do not exist. Not in this solution. For now. If you were in general chemistry, we'd dig deeper, but not right now. We just say that's the truth. No calcium sulfate ions in solution. It's all in the solid. So that means B is the answer. Okay? So this wasn't just write the proper equation, which you had to have, and the complete ionic equation. Right? That's a must. But learning how to take tests with that information is also essential for this problem. Eliminate things as you go, right? Reduce the number of choices you have to make. That's the most efficient way to take a test, particularly multiple choice. Okay, let me see if I got any more pictures in here. Let me be sure we get all the pictures, because they can give students trouble. No, that's the only one I got in there. Okay, now we can look at, let's go back up to, what, 150? Yeah, let's go back up to 150. Let's see. Okay. There's another one where you have to write the balanced equation and then break it apart into the complete ionic equation. You can do that. Classify these following. Okay. Classify the following. What do we have here? Start off with an H. That's an acid in aqueous solution. KOH. That's a base. And this is the salt that forms from that anion and that cation, and then water. So this is an acid-base reaction. Is there any oxidation reduction going on here? Nope. You can check it to be sure, but there's none. There could possibly be some type of acid-base reactions that are oxidation reduction, but they're rare. In this case, no. That nitrate remains whole, no changes there. That hydrogen is still +1, the hydroxyl is still -1, which makes this hydrogen a +1 and that one a -2. Same thing for water. There's no oxidation reduction there. There's no precipitation either. I don't see any solids there. There's no combustion. You don't have oxygen as a reactant. So the only one that's possible is acid-base. What type of reaction is this? Okay, you see you've got an element there, an element there. They're in compound here. Oxidation reduction for sure. But what other possibilities could there be? Well, two simples, a complex makes a synthesis. Right? Is there a synthesis here available? No. There's no precipitation. We don't have any aqueous solutions that form a solid upon reacting. It's not a double replacement. You have to have two binaries to have a double replacement. Single replacement, you have to have an element and a binary in order to do a single replacement. It's not there. The only possible one here is oxidation reduction. Let's see. You can do that one. I'm going to skip that. This is just to check your memory. When a metal and nonmetal react, the metal loses electrons. How do you know that? Well, if you look at our naming convention, the cations always come from metals. That means they're positive, right? If they're positive, that means they had to lose electrons. And nonmetals gain the electrons, right? All the halogens are -1, all the chalcogens -2, all the nicogens -3. Those are nonmetals. They gained electrons to get those charges. That's a repeat. How about this one? There's no oxidation reduction in this reaction. Just look at it. That lead 2 is the same. Lead 2+, and over here it's lead 2+. Sodium didn't change. sulfate is still there, sulfate is still there, which means the sulfur and the oxygen didn't change their oxidation state. The nitrate's the same on both sides. This is not oxidation reduction. It's not acid-base either. I don't see any acid or base in there. This is a precipitation reaction. It's also a double replacement, but that's not a choice. The only choice you have is precipitation. How about 105? Oops, excuse, too far. Look at this reaction. Ammonia plus oxygen. Combustion, which means redox also. Okay, those two definitely. Is it a synthesis? No. You got a compound and an element forming two compounds. Synthesis, you need elements, two elements to form the compound. Decomposition is definitely not that. It's just the opposite of synthesis. So the only two that work are oxidation and combustion. That's why you have A and B in here together. Let's see, what type of reaction is this? Okay, you have an element and an element makes a compound. That's a synthesis. But is that a choice? No. But you have an element on one side in a compound on the other, that's oxidation reduction. And there's no precipitation. Right? So oxidation reduction is the only possibility. How about this one? Mercury plus oxygen yields mercury 2 oxide. Just the opposite of Priestley's experiment. In fact, Priestley went to visit Antoine Lavoisier in Paris, France, and visited him to discuss their experiments. Lavoisier was not surprised by Priestley's results. Lavoisier had already come to the conclusion that oxygen was an element. See, there was a theory going around in Europe at the time that was dominating discussions. It was called the phlogiston theory, which was in the process of being discredited. And Priestley and Lavoisier were two of the scientists, among others, who were conducting quantitative experiments that blew phlogiston out of the water. So what Priestley did was he came to Lavoisier and said, this is what I've done. I've taken mercury 2 oxide, which they called something else at the time, and decomposed it into these two. And I got a gas. And this gas made you feel really good when you breathed it. Right? Oxygen gave you an oxygen high. Then they met for a while. And after Priestley left, Lavoisier sat down and put together some experiments. He says, all right, what would happen if I combined mercury with air? Because we think that this component of air will react with mercury. And sure enough, it did. And it produced this compound, and it had all the characteristics of the compound that Priestley had used when he decomposed it. And Lavoisier noted the reduction in volume of air required. And then he took that same compound and decomposed it in such a way that he could collect the oxygen and measure its volume. And he found that the volume in the first experiment was the same volume in the second experiment for oxygen. So he said, oh, there's only one way that can happen. Oxygen has to be a unique element that does the combination with mercury. And at that time, they call anything that combined with oxygen was called a calx. That's why the oxygen family is called chalcogen. Gen comes from the Greek for genesis, which means to make. So if they make a calx, they're chalcogens. That's why the oxygen family is called that. Okay, so this reaction is definitely oxidation reduction. Element makes a compound. It's not acid-base and it's not precipitate. It's also a synthesis, but that's not one of the choices. Okay, how about this one? Gallium nitride makes gallium and nitrogen gas. This is a decomposition, right? So D is possible. Can't be a synthesis because that's the opposite of decomposition. It's not a combustion, there's no oxygen there. But is it oxidation reduction? Oh yeah. Goes from compound to elements. There has been a transfer of electrons, no doubt about it. And notice it makes a metal and a non-metal. So which one got the electrons? Well, gallium had to get the electrons because it's positive in this compound, and now it's neutral. And nitrogen had to give up the electrons to go from -1, let's see, -3. Nitrogen went from -3 to 0. Okay. Let's see, I skipped one. How about this one? That looks like a huge mess of an equation, but it's really not. It's simple. This is an acid. See that leading proton? It's got other hydrogens in there, but those hydrogens can't dissociate. That's what makes it an acid. This one proton makes that acetic acid. And this hydroxyl makes that cesium hydroxide a base. Acid, base, makes water and salt. So that's an acid-base reaction and nothing else. Let's skip that one. There's another acid-base. Okay. KBr is soluble. Potassium bromide. Silver nitrate is soluble. Silver combines with the bromine, forms a solid. That's a precipitation. And then what's left over is spectators. Precipitation of these choices is the only one. It's not acid-base. There's been no oxidation or reduction. So precipitation is the only one that works. We've done one like that. We've done one like that. Okay, how about this one? Zinc and hydrochloric acid. If you ever drop a piece of zinc in hydrochloric acid, you'll find out quickly that there is a chemical reaction going on there because gas will form. And that gas is hydrogen. Okay, so when that hydrogen forms, how do you know it's hydrogen and not something else? Well, based on the reaction, the balanced equation, you assume that it's hydrogen. But one way to test it when you observe the reaction is to capture the gas, right, in some sort of container. And if you do that, then you can determine, is the gas, there are three types, right? There are flammable gases that will burn, right? And if you put a glowing ember into that gas, as long as oxygen can mix with it, it'll pop, right? It reacts, it burns. Or the gas can support burning. So if it's oxygen or nitrous oxide or some gas that can support burning, when you put that glowing splint in, the splint will catch fire. But it won't pop, it won't burn the gas, it supports the burning of the splint. And the other type is it quenches flame. So say if the gas is carbon dioxide, for instance, you put the glowing splint in there and it goes out. It is dead. No more glow. So those are three types of, the three tests that a glowing splint will give you when testing a gas for its qualitative nature. So this says that we've changed from a zinc metal to a zinc in a compound. That's oxidation reduction. Definitely. It's not an acid base. There's no precipitation going on here. let's see, 116. I better keep track. We got another 45 minutes. Be sure I get to all the topics that I want to do. Yeah, we've hammered the types of reactions pretty hard. That should be enough. So let's look at some more balancing equations. Let's see, where are we? Here we go. This one should be fairly simple. The real trick to this one is writing the compounds correctly. That's the key to 125. The balancing part will be easy if you use my helpful hints. So it's saying lead 2 nitrate reacts. Lead, and it's a 2+ charge, combined with nitrate, which is a 1- charge. So we need 2 nitrates. And that's an aqueous solution. Right? And then combine that with aqueous sodium iodide. Sodium iodide. -1 + 1. That's balanced. And it's in solution. Now what do you get? When you put those solutions together, all you have to do is a double replacement. Sodium with nitrate. Sodium with nitrate is soluble. It's aqueous. Lead with iodide is a solid. Look it up in your chart, in your solubility chart, and you'll see that lead iodide is a solid. So now we just need to balance, right? We've got this polyatomic here that we can hold together. We've got 1 lead, 1 lead, 1 iodine, 2 iodines. So we need 2 here. Now we have 2 sodiums. We need 2 sodiums. 2 sodiums, 2 nitrates, 2 nitrates. See, these double replacement reactions, most of them, are very easy to balance. And that's what the balanced equation looks like. Let's see, how about let's see, these are all too easy. Okay. How about 135? Here we go. All right, 135 and then 136. And then I think 137. No, 137 is different. I'm going to take 135, 136 and expand on it. So 135, 136 are based upon the same equation. What we're given is a word problem that says barium hydroxide is mixed with sulfuric acid. Wait a minute, that's not, we did that one already. Sorry. I didn't realize that was coming up. We did that one earlier. The one that forms a precipitate. Acid-base reaction that forms a precipitate. Right? So we don't need to do that one again. Let's do 138. So scroll down a little bit. 138. Let's take 138 and take the word problem, right? Just Put your blinders on, don't look at the answers. The word problem says we want the molecular equation, the complete ionic equation, and the net ionic equation for this reaction. Aqueous copper 2 nitrate. Copper 2 nitrate. This is a 2 plus, that's a 1 minus. So we need 2 of those. Reacted with sodium hydroxide. Sodium hydroxide, -1, +1, aqueous. So we swap sodium and nitrate. As aqueous, plus hydroxide and copper. And since this is a 1 minus and that's a 2 plus, we need 2 of those. And that's a solid. Here we go. Keep it on screen. All right. So we've written the compounds correctly. We need to balance them. Balancing should be easy. 1 copper here, 1 copper there, no problem. 2 nitrates. We need 2 nitrates over here. Now we need 2 sodiums here. All right? That gives us 2 hydroxyls, and 2 nitrates, 2 nitrates. We're good. That's balanced. Now the complete ionic equation, after the molecular is balanced, you break it apart into ions. So copper, 2 plus, aqueous. 2 nitrates, aqueous. Why? Because that subscript says there are 2 of them. 2 sodiums and 2 hydroxyls. Now on the product side, we still have sodium and nitrate in solution, right there. We have 2 sodiums, and that's aqueous, and 2 nitrates, aqueous, plus the solid. That's the complete ionic equation right there. Scroll down, there it is. All right. Now, how do you go from there to the net ionic equation? You remove the spectators. Cancel the spectators. Where do you have spectators? Well, copper's in the solid. It's not a spectator. Hydroxyl's in the solid. We have to keep it. Nitrate, 2 nitrates on both sides. And 2 sodiums on both sides. Now we write the net. Copper, 2 plus, aqueous, plus 2 hydroxyls, aqueous, yields copper hydroxide solid. Okay? That's the net ionic equation. Now, why do we want to know the net ionic equation? Well, for theoretical reasons, that's what's driving the reaction. Spectators don't have anything to do with it. But for a practical reason, suppose you want to conduct this reaction and get that solid, but you don't have sodium hydroxide. Maybe all you have is potassium hydroxide. You can use potassium hydroxide here. As long as you get the hydroxide in here, you've got a reaction. Copper nitrate, right? Maybe you don't have copper nitrate, copper 2 nitrate. Maybe you have copper 2 chloride. It'll go into solution as long as you get that copper in there, and you still get the same product. Okay, let's see. Oh, that's it. That's all I have. We're better than a half hour finished. Let me see if there's, I had some others that I might want to do. Balancing equations. Let's see. We did that one already. Yeah, we did that one already. Ooh, this is a... All right, let's try this one. This one's not in the document. So I'll unshare that in just a second. We don't need to share the screen anymore. Stop the share. And there we go. Now we can get a full screen of this one. Now this one could be a problem. And I'll explain why in just a second. Ammonium nitrate. Right? You've heard of ammonium nitrate. That's the stuff in combination with fuel oil that brought the Alfred P. Murrah building down in, where was it? Oklahoma? Timothy McVeigh and company mixed that up with fuel oil and blew that building down. That's why it's restricted. If you're not a farmer, you can't get that in large quantities. Okay, that, we're going to decompose it in a manner of speaking. We're going to break it down. And it produces this one, right? No, that one, that's nitrous oxide or dinitrogen monoxide, laughing gas, and water. Water. There we go. And now we want to balance that. Here's the problem. This is what's called a disproportionation reaction. In that type of reaction, the same element is both oxidized and reduced. Now that sounds like a contradiction. You can't do the same thing on the same element at the same time. Well, you can, but you can't do oxidation reduction on the same atom at the same time. But in our formula, suppose one of these nitrogens arrived here from an oxidation and the other one arrived here from a reduction. That's possible. So let's see what our oxidation states are. This nitrogen, that's a +1 here and a -2 for oxygens. So that's a -6, and this is a +4. Well, let's take them separately. That works better. What do we have here? This is a nitrate, right? So if this is a 2- and it's a 6- total, and the combination has to add up to a -1, we really only need a 5+ here. Right? A 5+ and a 6- is a 1-. So this is a 5+ for that nitrogen. How about this nitrogen? Well, we have 4 pluses from here, so that means this has to be a 4-. Okay, so that's a 5+ and this is a 4-. And they're both going to end up over here. Well, one of them's going to end up in one nitrogen, and the other one's going to end up as the other nitrogen. So what's the oxidation state here? Well, they both can't be different. They're both the same. So this is a 2-. That means this has to be a 2+ together, and each one of these has to be a 1+. Okay, now we have our oxidation states. So this one is going to go from here to here. How do you get from 5+ to 1-? You gain 4 electrons. 4 negatives cancel 4 negatives and leaves you with 1+. So you gain 4 electrons per nitrogen. In this one, you have a loss of how many electrons? Well, if you lose 4 electrons, you're neutral. If you lose another one, you're 1 plus. So it's actually 5 electrons. Loss of 5 electrons per nitrogen. Okay? Now, like I said earlier, the number of lost electrons has to equal the number of gained electrons. So, if you gain 4 electrons and you have 5 electrons here, then you've already got, well, you got one of them here, actually. One of them there. So, let's see. I'm thinking just for a second. We're actually missing 1 electron somehow, right? Because we went from a 4 minus to a 1 plus and a 5 plus to a 1 plus. 4 electrons, 5 electrons. Okay, so we've got an even and an odd. So normally what I would do is cross multiply. I would say 4 times this and 5 times that. You know what? We may not have to do this, right? This is a disproportionation reaction, but some of them you can balance without considering the electrons. Let's try that. But keep that there. And let's just say we have nitrogen, nitrogen, hydrogen, and oxygen. So we have 2 nitrogens here. We have 4 hydrogens. We have 3 oxygens. And over here we have 2 nitrogens. We have 1, 2 oxygens. And we have 2 hydrogens. So, nitrogens are good. Hydrogens, how about that? If we need 4 hydrogens, we put a 2 here, right? So what does that do? That makes 4 hydrogens, and 2 plus 1 is 3 oxygens. Okay, that was easier than I expected. I didn't need to do oxidation reduction to get there. Okay, let's see if there are any others that I'd like to mess with. Let's see. That one's too. That's a mess. I'm not going to do that one. That would be just plain evil for me to do that one. I think that's enough. Yeah, that's enough for now. Okay, any questions? So on Thursday, excuse me. So on Thursday, we'll have an exam on these 2 chapters, whenever you want between now and Thursday. And then Thursday in class, we'll go to chapter 9. We already done chapter 8. We did that one first and then came back to 6, 7. Now we're going to do chapter 9 and learn how to determine quantities of reactants and products using a balanced equation. We had to learn how to balance equations first. Now we can, now we know we're going to find out what to do with them. Because we don't just stop here at balancing equations. We balance equations so that we can conduct experiments and predict outcomes, or design experiments with how much do I want to put together reactants to get a certain amount of product. That's the question. That's the question. When you answer it, it makes you money as a chemical engineer. Okay, any questions, comments? We'll cut it off a half hour early.